Predicting heart attack risk through patient metadata. According to the CDC, heart disease is the leading cause of death for Americans. Smokers were much more likely to have a heart attack, often developing a cardiovascular disease 5 years earlier. Men were 1.5 times and women were 2 times more likely to die from that first heart attack. In simple terms, a heart attack is caused when blood flow is blocked, with many of the variables causing it being related to physical and genetic traits. A previous project done at UCI created a model where they attempted to predict heart attack outcome from a multitude of variables, with the more variables used, the more accurate it was.
Our research question is, how likely is an American to suffer from a heart attack based upon measured physical health traits? These traits include age, gender, cholesterol, BMI, smoking status, diabetes, and physical activity levels.
So for our hypothesis, we predict that high cholesterol, BMI, smoking, diabetes, low physical activity, gender, and age will make individuals more likely to suffer from a heart attack.
Our dataset was from Kaggle called Heart Attack Prediction in the United States, which had over 300,000 observations, each representing a different patient. We chose 7 different variables that we mentioned earlier in our hypothesis. We're comparing these variables to the outcome column, which told us if they actually had a heart attack or not. Some of our data visualizations. Our first one is a distribution of all the BMI ranges inside of the dataset. You can see that they're pretty spread out, with many of them, and including the average, outside of the normal BMI range. Additionally, you can see that BMI does not really have an outcome compared to if they had a heart attack, with yes and no being pretty split.
So for this graph, we had BMI plotted against cholesterol, and we can see that there's a slight upward trend between these two variables. This is expected from us because we expect there's an upward trend. However, we expected it to be steeper, whereas this one has a very subtle change. This may be attributed to the idea that cholesterol consumption may be similar across all BMIs. It might be due to more other confounding variables like metabolism speed or muscle mass.
This is a correlation heat map of all the health features against one another. Noticing a lot of the zeros, it means that most of the variables don't exactly correlate with one another, and if anything, just correlate with themselves. And now we're going to look at our data analysis and results. For our data analysis, we created 4 models, 2 of which are simple logistic regressions and 2 of which are hypertuned. In our first set of regressions, we used features that we had chosen in our hypothesis, and we yielded a 50% accuracy rate and a recall rate of 41%. In the case of heart attacks, recall is an important number to know because these are the cases where an actual heart attack occurred based on what was actually predicted. In the second set of regression, we used features that had the best p-values when we had permutation tested against our results column. It once again yielded a 50% accuracy rate, but the recall improved to 45%, which is an improvement in the way our model predicts the unseen data. All of these models went through a thorough series of cross-validation and hypertuning to achieve the best hyperparameters and results.
In conclusion, our most significant variables associated with heart attack occurrence were previous heart attack, stress level, cholesterol, and gender. These variables only partially supported our hypothesis. Our prediction model achieved a 50% accuracy level with a 50-50 chance of predicting heart attack outcomes. Our current model is unreliable because if the model has a false negative, a patient may be detrimentally undiagnosed. Our major takeaway is that the original dataset is too refined and therefore limited our ability to create an accurate and reliable prediction model. For future study, we need to use multiple diverse datasets to increase our data scope and make sure it's not limited.